In a previous video, I was describing a pulse code modulation technique and using this circuit to basically demonstrate some of the features of the analog discovery. In the course of that, I had to, of course, make a number of assumptions about the viewer's knowledge of various electronic circuits, especially digital logic circuits, things like flip-flops and inverters and so on. What I would like to do in this series is produce some hopefully short videos on digital logic, starting at the basics. In other words, not assuming that the viewer knows how digital logic works and would like to learn, or learned it once upon a time and would like a review of what they know. So whether you're interested in following a circuit of this sort, or maybe you see a description of a device in a data book that includes some strange looking symbols, or whatever your interest is, I'm hoping this series will be useful to you. If you feel like that you understand digital logic, both combinational and sequential, then I would suggest you don't need what we're going to be covering here. The purpose of this is going to be to bring people up to speed who perhaps have never had the advantage of a digital logic circuit course or studying it in some other format. In case you're a little bit intimidated by the idea of learning digital logic, I will have to say you actually already know a lot of what you need to know to understand computer logic or digital logic. I, however, do want to make a distinction between arithmetic and logic. And here I've used a couple of examples that later will become clearer why we make this distinction. With arithmetic, there are a couple of basic operations. Actually, most people consider them to be four: add, subtract, multiply, and divide. However, as you know, the only difference between divide and multiply is one is the reverse of the other, and the same with addition. Subtraction is just the addition of a negative number. So we're going to just look at when you do a simple arithmetic, you add numbers. Sometimes, however, when you add a couple of numbers, you get a carry. And so let's keep that in mind, that you know how to add up numbers. These are decimal numbers. You also know how to multiply decimal numbers. Once again, you multiply the 7 by the 3 to get 21, and then the 2 by the 7 to get 14, and then you add them up. So in your mind, you have tables that let you do this kind of operation. You may not realize it, but you basically have a lookup table in your head for addition and for multiplication. Logic, on the other hand, is generally the application of some simple principles. Suppose, for example, that you are choosing sides in basketball, and Bill and Mary are equally good at basketball. Well, you might say, well, I'll take Bill or Mary. Now, that doesn't mean that you will get both Bill and Mary on your team, but you want one of them on your team, one or the other. There's a possibility you might get Bill and Mary, and that's this next example, Helen and John. Suppose that Helen has a certain set of skills and John has a certain set of skills, but they're not the same skills, and you need both. Well, then what you would like to do is you would like to Helen on your team and John on your team so that you have their total skill set. This is logic. In a little bit, you will see that when we go into the binary world, these two sometimes get confused. It's not a big deal, but keep in mind that arithmetic and logic are not quite the same thing. Now, a minute ago I said you have in your head lookup tables. Here, for example, is a decimal addition lookup table. And it's everything you need to know to do decimal arithmetic. It's very simple, of course. When you're doing addition, 0 plus 0 is 0, and 0 plus 1 is 1, and so on. The maximum you can get in this case is 9 plus 9, which is 18, and 9 is the largest decimal digit, so that's the biggest number you can get in this lookup table, and you have this in your head whether you realize it or not. Similarly, in your head you have a decimal multiplication table. And here you see that you multiply 1 times 1 is 1, 2 times 1 is 2, and so on. Now, when you're doing multiplication, as we saw in that first example, there are occasions where to do multiplication of multiple digits, you need to also add. That is, you multiply, and then you add. That's exactly the same way that a computer does arithmetic. Furthermore, you may remember that when you're doing addition, 8 plus 2 is 10. Now, what you may not realize is that basically says 8 plus 2 is a 0 with a carry of 1. When you're doing multiplication, there's no such carry in and of itself, but there is an implied carry. In other words, 5 times 4 is 0 with a 2 in the next decimal place. That may all sound like just simplistic, but in binary arithmetic, that is, in arithmetic in which the only symbols you have are zeros and ones, what you are doing is you are restricting yourself to this part of the table. It's exactly the same as decimal. In other words, 1 times 1 in binary is 1. 0 times anything is 0 in binary, just as it is in decimal. The difference is you don't have the numbers 2, 3, 4, all the way up to 9. So in binary, when you're doing arithmetic, this is the table you use. Notice once again that here the 1, 0, that's not 10, that's 1, 0. It's important to read it that way because a binary 1 plus a binary 1 produces 0 with a carry of 1. When you're doing multiplication, in binary, we also call this the AND operation, and that's why I've written the multiply symbol and the dot. This is just the same, it means the same thing. In binary, 0 times anything is 0. The only time you get a 1 is when you multiply a 1 by a 1. But once again, remember in our earlier example, where we said that logic is not the same as arithmetic. And here's the difference. In logic, if we OR, remember this is like Mary or Bill. But there is also the possibility that you will get Mary and Bill, which is this one. In other words, the OR operation says we get, if there's a 1 on the input, then the output will be a 1. It doesn't matter whether the 1 is on this input or both inputs. In other words, an OR operation in logic uses this table. The AND operation, you may notice, is exactly the same as the arithmetic multiply table. In other words, whether this is a 0 or a 1. If it's a 0, the output's a 0. If the input of this one is a 0, the output is a 0. Only if both inputs are 1 do you get a 1 on the output. So we are going to be using these tables again and again in what we're going to do. But at this point, I'd like to break off and use this as part 1. It may seem very simple, but recall that you're basically doing everything that is done in a digital computer. All digital computers do is logic operations and arithmetic operations. Now, in the next part, we'll talk about why we choose binary arithmetic for computers instead of decimal arithmetic.